Good morning to all of you, and I welcome you all to this very first lecture on the course titled Conduction and Convection Heat Transfer. Before I provide you with the detailed contents of the course, I like to tell very briefly what the subject heat transfer is and what is its implications, relevance or importance in practice. We have already been aware of the word heat in thermodynamics. Heat is a form of energy in transit, means which is recognized only in flowing condition, that means energy which flows or being transported due to a temperature difference, and it flows from a high temperature to low temperature. So, temperature is the potential for heat, the energy in transit to flow. In thermodynamics, we have observed that the quantity energy has got two distinct status. Thermodynamics has taught us that the quantity energy has two distinct status. One is the energy in storage, where the energy enjoys the characteristics of a property and it becomes a point function, that is energy stored in a system. And another is the energy in transit, that means the energy which takes place in transit when the two systems interact with each other. And there are two forms of energy that appear in the form of energy in transit, which behave as a path function. They are work and heat. And heat is that kind of energy in transit which is transferred because of temperature difference from high temperature to low temperature. Now, thermodynamics deals with systems at equilibrium states, and when system undergoes a process from one equilibrium state to other equilibrium state, thermodynamics tells us what is the amount of energy interactions with the surrounding or with another system by virtue of which it undergoes a process, and that is also related to the energy stored by the system in the perspective of the conservation of energy, which is precisely known as first law of thermodynamics. But where thermodynamics fails is to determine the rate at which this energy will be transferred. How much time will be required to transfer the energy from one equilibrium state to another equilibrium state. In classical reversible thermodynamics, the concept is such that system undergoes from one equilibrium state to other equilibrium state through a series of equilibrium states where the process is quasi-static or reversible and time taken is infinite. But in practice, we have to transfer a quantity of heat within a given interval of time. So, therefore, what is most important information in this regard is the rate at which heat is transferred between a system and another system. So, the rate is to be known so that we can find out the time taken to transfer a given amount of heat, and accordingly we use this information to determine the size of the equipment required to accomplish this process. So, therefore, information on the rate of heat transfer is very much important, though we know the definition of heat and also the definition of temperature by thermodynamics. Temperature is defined by the zeroth law of thermodynamics, as you know in classical thermodynamics, which tells the ability of a system to be in thermal equilibrium with another. So, though we know the heat and temperature from thermodynamics, but what is the rate of heat transfer and how is it related to this temperature difference is the gamut of heat transfer. Now, therefore, we see that heat is transferred because of the temperature difference. Since the classical thermodynamics deals with the equilibrium state of the system, we always tell this system of given temperature. But when the system is not in equilibrium state, there may be temperature differences within this system. So therefore, heat can flow within this system from one point to another point when there is a temperature difference. So therefore, we can summarize this as heat is an energy in transit that flows or being transported by virtue of the difference in temperature between 2 points in a system or from one system to another because of the temperature difference in this system. Now, I tell you the heat transfer, the subject heat transfer deals with these rate equations, the equations that predict the rate of heat transfer, and through this some property is defined by the media of the medium that allows the heat to be transferred. This property is thermal conductivity. Many other properties are also associated in determining these laws and equations for heat transfer. So therefore, this subject describes quantitative laws for heat transfer along with the definition of those properties defining these laws and their changes. Now I come to the importance of heat transfer in practical life. In fact, heat transfer is involved in entire science and engineering and biological systems everywhere. You start from this, that the growth of human being, the growth of trees, plants, growth of animals all depend upon the heat transfer process. If you think simply what we do daily, our human activity, we take energy through food, and that energy after the metabolism within our body generates energy which allows the blood to flow to the arteries, makes the organs alive, by virtue of which we are able to do work, and at the same time that makes our skin hot, high temperature. Skin arrives at a high temperature. Then to make us comfortable, we have to transfer the heat to the ambience. So ambience has to be conducive enough so that the heat is transferred and the human surface of the human body is kept at a comfortable temperature. So this way there are all activities for our growth, for our daily activities are involved with the process of heat transfer and also mass transfer. I am not going into that details. Now let me come to our engineering applications. In engineering, heat transfer is deeply involved in all sorts of applications. If you first see the power industries, you know that we develop mechanical and electrical power that is needed for manufacturing products, for electrifications. All this power is being developed from the natural energy resources, and more than 70% of the power today is the global statistics is being developed from burning the fossil fuels. And what is done is the fossil fuel is burned, and after burning, because of the exothermic reaction, a huge thermal energy is generated, which results in a very high temperature, hot, that means high temperature products of combustion that is used as a heat source to transfer heat. And you know from thermodynamics that if you have to have continuous mechanical power out of this type of thermal energy, what you have to do? You have to transfer heat to a working system which executes a thermodynamic cycle, and you have to also reject heat by this working system to another system while working in this cycle. So therefore you see here the heat transfer processes come in, where the heat transfer, heat is added to the system, working system, where heat is rejected. This, if you recall your thermodynamics, you know that in a conventional steam power plant, this heat added portion is done in boiler, where the heat from the flame and the combustion gases is being transported to water. So, for efficient transportation of heat and to design the furnace, design the water walls of the boilers, we have to know the rate of heat transfer. Here also the phase change takes place, the water boils. Similarly, the steam coming out of the turbine is being condensed in the condenser by taking the water from the ambience as the cooling agent, circulating water, water circulates, takes the heat, where the heat rejection takes place by second law of thermodynamics. So, therefore, to design a condenser, its size, we have to know the rate at which steam should reject heat to the water. So, therefore, you see these are the heat transfer processes. Similarly, in case of gas turbine engines, where the combustion product itself works on the turbine, but after coming out from the turbine in a closed cycle gas turbines, these gases are being cooled by an heat exchanger by using cold air from the ambience. Well, again in a recycling system, in case of steam turbine, this water which takes the heat from the steam is again being cooled in a equipment known as cooling tower by using the ambient air. Similarly, this heat exchanger which cools the hot products by the ambient air is also being cooled by another equipment, another heat exchanger. So, therefore, you see the heat transfer processes are inherent to the power producing devices. In a nuclear reactor, the similar thing is there. There are other places where heat transfer is very important, which is also related to the power production equipment or devices, where the temperature is becomes so high because of the generation of thermal energy, though colloquially many places we use heat generation, but this has a contrast. A pure thermodynamist will not allow it, because heat is not a stored energy which can be generated and stored. So, it is the generation of thermal energy. Heat transfer comes when it is in transit. We allow the energy to flow by virtue of temperature difference. So, therefore, as much as possible, I will try to tell generation of thermal energy. So, generation of thermal energy makes the system so hot, it has to be cooled, otherwise the metal will not sustain that high temperature, which happens in the engine of a reciprocating internal combustion engines, that cylinder of our automobile engine, where the fuel is injected in the air and the burning takes place, and because of that exothermic combustion reactions, energy is generated so that the cylinder wall becomes very hot. What is required is the effective cooling of the cylinder wall to maintain its temperature so that it can work well. For that, effective cooling system is made. Again, the water which is used to cool the cylinder is again being cooled in a radiator to have a recycling system. This is a cool. Nowadays, the coolant is used for effective cooling. Similar thing happens in a combustion chamber. Combustion chamber where the burning takes place, we have to cool the combustion chamber so that the combustion chamber wall can sustain it. These are for your popular knowledge. Probably you do have all this information today. Another very interesting thing is that for gas turbine power plant or steam turbine power plant, finally what happens, the high temperature steam in steam turbine power plant coming from the boiler, or a high temperature burning products in case of gas turbine power plant coming from the combustion chamber comes to a steam turbine to develop work. And steam turbine is a typical turbo machines which works on the principle of change of angular momentum of this fluid while it flows through that and develop power. And basically it has some blades mounted on a shaft which is rotating, and these blades fail miserably if the temperature of the fluid flowing through it is very high, and that mode of failure is known as creep failure. To avoid that, there is always a restriction of the inlet temperature at the turbine blade, but we cannot reduce the inlet temperature of the steam or gas to that level so that turbine maintains its temperature well below the creep failure. So, what is done? So, effective cooling of the turbine blade is made, and that is entirely a different subject, that cooling of the turbine blade. So, therefore, you see in the power industries, heat transfer is totally involved. If you come to the process industries, in all process industries in manufacturing products, we require some part heating of the materials, somewhere cooling of the materials. I am not going into that details. For example, a spray drying things where the products are made by spray drying. The solution is sprayed into a chamber or dryer where the hot air is allowed to flow and which allows the solvent to evaporate so that the dry product comes out. This is one example. There are a number of process industries where heat transfer is associated with. Next, we come to a very, very great application of heat transfer is the electronic industries. Today, we are proud of our advent in the electronic industries. The invention of electronic chip, VLSI, large scale integration, all these miniature electronic circuit boards could not work successfully if they could not have been cooled. This is because of what? That is small electronic components in the development of VLSI. They dissipate electrical energy in generating thermal energy. For what? The electronic component becomes hot, but at high temperature the electronic component can perform their function. They are inoperative. So therefore, what is most important to make this electronic component cool, depending upon the circuit board or the component, we may cool it naturally by putting it into the air, or we may allow to flow air to cool it. So this design of this circuit board and the cooling system, in this case for cooling we use semiconductor, that I will tell what is a semiconductor for cooling purpose. So therefore, all electronic components, electronic circuit board cooling is extremely important. Sometimes a fan is given, sometimes we take the help of the natural convection, but we have to know the equations, we have to know the laws, principles, so that we can tell yes, the fan will not be required. Okay, it's okay. In the natural ambient condition, it will be automatically cooled to the temperature below the operative level. So this way you see that heat transfer is involved in electronic industries. In biological system, heat transfer is very much involved because our entire biological process along with our growth is involved with heat transfer, and scientists are utilizing this in the applications, those who are involved in the development of healthcare systems. In the microfluidic research, a lot of heat transfer studies are being done for the application of the to the biological systems. So with this in our background as the definition of heat transfer, then overall understanding of the gamut of heat transfer and its practical relevance, now I will show you the course contents. Now course contents, when I show you, I tell you this is an introductory course on conduction and convection heat transfer. We will emphasize the underlying fundamental concepts of these two modes of heat transfer, conduction and convection, and we will enumerate the laws, principles and the governing equations based on derivation from fundamentals. The coverage, I tell you, will be well balanced with physical concepts, analytical operations, along with examples and exercise problems of practical importance. And I am sure that after completion of this course, a student will have a strong foundation on this conduction and convection heat transfer and will be competent enough to apply the laws and equations appropriately to practical scenarios. This is the learning objective. Now, my job is to tell you about the detailed content of the course. In fact, this course will be taught by both of us, myself and Professor Sumon Chakraborty, and I introduce the teaching assistant, Mr. Sayan Das, who is a research scholar. You come here and show your face, and Mr. Shubhodip Mondal. Shubhodip, please show your face, the students must know. that Mr. Shayan Das and Mr. Shubhadeep Mondal. The next one. Konta? Huh? No, this. Now this is the course content. Just I tell you hurriedly, this course is divided into basically 3 modules. The module 1 is the conduction, and this is a tentative schedule. We will try to follow as much as possible this schedule. Introduction and fundamental concepts, which will be given for first or for 2 lectures. Then derivation of heat conduction equation, discussion on boundary and initial conditions. Then one-dimensional steady heat conduction, different configuration, plain wall, cylindrical wall, spherical wall, with and without heat generation. Again, this is a very conventional but colloquial and truly speaking incorrect statement. Heat cannot be generated. Heat is an energy in transit. Sometimes I ask this question to the student. Just I tell you now, since all of you have completed the thermodynamics course, you have an insulated vessel within which there is a reactant reacting. You make a spark or initiate the reactant. What happens? The temperature becomes high, but a colloquial statement said heat is generated. Where is heat? It is insulated. No, heat is transferred. Where the heat is transferred? That means it is the generation of thermal energy because of the exothermic reaction which makes the product hot. If you remove the insulation, then only heat will come. If I stand by the side of a reactor, huge reactor, and hugely insulated, I don't find any heat transfer. I don't find any heat coming to my body. So why the heat is generated where it is gone? It is the thermal energy that is, no sir, heat is generated and it is stored in this system. Heat cannot be stored in this system, it is not a stored energy. The thermodynamics teacher will be very annoyed. So therefore, it is the generation of thermal energy, not the heat, but colloquially people tell conventionally, that's why I am telling with and without heat generation. Concept of critical thickness of insulation, heat transfer through extended surfaces, fins, 2-dimensional steady state heat conduction in plane wall, analytical approach, unsteady heat conduction, lumped heat capacity system, 1-dimensional transient heat conduction in infinite plates and semi-infinite solids, analytical treatment. This is the topic of the conduction, and then it will be followed by an assignment of questions and solutions with discussions. Second module is the introduction to convection and review of fluid mechanics, and this include topics physical mechanism and fundamental concept, because the convection mode, I will tell you afterwards, is not a basic mode of heat transfer. It is the conduction which is the basic mode, which is affected by the flow of the fluid. That's why the name convection comes. So therefore, in the convection, the first part we will make a review of fluid mechanics that you have already studied. After the physical mechanism and fundamental concepts, we will go for recapitulating the fluid dynamics, that is derivation of Navier-Stokes equation, exact solutions, plane Poiseuille flow and Hagen-Poiseuille flow, concept of boundary layer, derivation of boundary layer equation, boundary layer over a flat plate, solution by integral method, boundary layer separation. Then uploading of sample questions, solution, discussions with MCQ problems. Next, the third module is the continuation of the convection, and there are 2 types of convections which will be told in detail afterward, forced and natural convection, derivation of energy equation, identification of dimensionless term. Then concept of thermal boundary layer and derivation of thermal boundary layer equation. Then thermal boundary layer over a flat plate, energy integral method, brief description of other types of flows, flow past cylinder and spheres. Internal flows, concept of thermally fully developed flow, solution for thermally fully developed Hagen-Poiseuille flow with different boundary conditions, constant heat flux, constant wall temperature. Then the natural convection part, we will teach Boussinesq approximation, vertical heated wall, scaling analysis and scaling laws in terms of pertinent dimensionless number. Then uploading of sample questions and solutions, discussion, MCQ problems with model solutions. And the last part of the last module or the last part of the course is on application side. That means after that, okay, sorry, there is a condensation, it is a basic thing, derivation of Nusselt's equation, and the boiling phenomena, explanation of boiling phenomena and pool boiling curve. These two will be taught in brief. Then the application, mainly the heat exchangers, types of heat exchangers, LMTD, log mean temperature difference, epsilon NTU expression. Epsilon is the effectiveness, NTU stands for number of transfer units. This just for your information, you don't know anything, this will be taught, that what the abbreviation is for parallel flow and counter flow shell and tube type exchangers, and this will be followed by uploading of sample questions and solutions, then discussion MCQ problems with model solutions. So, next is the reference textbook. First of all, I tell you, any textbook will do. I or Professor Suman Chakraborty will not follow a textbook in ditto. What is my suggestion? That classroom will be substitute of your textbook, not in 100%. You must read a textbook for follow-up, which contains these things, which are taught in the class. All textbooks are equal. If you understand things in the class, any textbook will be supplementing your concept. But as a reference, we list these textbooks: Principle of Heat and Mass Transfer, 7th edition, Frank in Cropera. It's a very good book along with other authors. Introduction to Heat, this is published by Wiley. This is a textbook by me. This is published by PHI Learning, the Prentisol. And another heat transfer is Basic Approach by OGC. There are a number of heat transfer books. Any book you can see, we will not follow a particular book. We will take problems from any of these three books, from other books also. So, you take any reference textbook, just for the sake of showing the text in a priority wise, we have shown this text. That does not mean that we will rigidly follow this text. Okay. Now, I start a subject with these things in backdrop. The overall understanding that what the subject gamut is importance and the course contents. Now, I start the subject. Now, conduction is there are basically three modes of heat transfer: conduction, convections and radiation. Incidentally, in this course, conduction and convection heat transfer, radiation will not come into picture, conduction and convection. Now, between these two modes, conduction is the basic mode of heat transfer. Convection is not a independent basic mode, it is artificially conceived by us. I will tell you in detail the concept of convection heat transfer. Convection comes into picture when there is a flow. It only occurs in case of heat transfer through fluid, where the flow can take place. And because of this flow, the conduction phenomena is affected, the basic mechanism of heat transfer. So, therefore, this affected convection, that is flow affected conduction, we define artificially as a different mode of heat transfer as convection, though convection is not a basic or independent mode of heat transfer. This particular thing you can write. There are certain things you must write, there are things which you may not write or may write as note, but this is very important thing. Though we tell two modes of heat transfer, conduction and convection, but basic mode of heat transfer is conduction and radiation, which is altogether governed by different physics and which is not included in this course of conduction and convection heat transfer. Now, conduction is associated with a temperature difference, I already told. Whenever there is a temperature difference between 2 points in spatial coordinates, the heat is transferred because of conduction. So, therefore, a temperature, continuous change of temperature comes into picture and it flows in the direction of decreasing temperature. That means in the direction of negative temperature gradient. Let us think in this way, that let us consider a direction of heat flow Q. Q is flowing in this direction, and we prescribe this direction as x as a spatial coordinate. Well, and heat is flowing in this direction means there is a continuous change of temperature in this direction in any medium. Conduction can take place in any medium, and conduction is the basic mode of heat transfer in solid, in fluid, in static fluid, in flowing fluid, doesn't matter. All these things I will be telling in deep with concept. Now, if we have a temperature field which is a function of x only, x is a space coordinate I give in the direction of the heat flow, and if I make an ordinate t here, I can show this like this, t is a function of x. So therefore heat is flowing like this. Now if I take a cross section, a section at any distance x at ax from the reference origin or reference frame, then what happens? Heat is flowing across this section. Now here one thing is very important, when we define the heat, we define its direction. Heat is flowing in one direction. Okay. Now why I have taken an area normal to the direction? This is because in this connection we define a quantity heat flux. Now one thing is true, that what is the amount of heat that is flowing in a direction, to know that we have to know an area over which we are interested, the heat transfer, across which the heat transfer is taking place. If the area is more heat transfer, area is less heat transfer. So an area is important. So in this regard, a heat flux is defined Qx, which is defined like this, that if the total heat transfer through an area Ax, a finite area, I prescribe a finite area Ax, is Q, then Q by Ax limit Ax tends to 0. Now it is very fundamental and basic, like the stress, that the heat transfer reduces to 0 when A reduces to 0 at a point, but their quotient attains a finite value, limiting value, and that is the heat flux, that is the amount of heat per unit area, and therefore this gets a definition at a point. That means here we have heat flux at a point. So therefore different points we have different heat flux. It may be constant, may not be constant at all points on this area. If it is constant, then simply we multiply the area with the heat flux, gets the total heat flux across the surface. But what is the difference with stress? Stress is a second order tensor. When we define stress, force per unit area, the area may be normal to the direction of force, may be along the direction of the force. But while defining the heat flux or heat transfer, it is used as a vector in a particular direction, and heat flux is defined divided by the area normal to the direction of heat flow. You understand? So heat flux is the heat transfer divided by the area. This Ax has to be normal to the direction of heat flow. So heat flux this way takes the birth. You have to know every physical quantity from its birth. Then step by step you will have concepts. Sometimes somebody starts giving the definition, conceptual definition from little step ahead. It's nothing wrong. It depends upon the circumstances. But when you teach somebody, you start from this, that this is the definition of heat flux, which is defined at a point like a stress, that is the heat flow per unit area normal to the direction of heat flow. If you this way define the heat flux, then this heat flux, for example here in the direction of x, Qx can be written by an equation, widely known, widely popular equation, and we are grateful to the great mathematicians or physicists of France, name is Joseph Fourier, who from his experimental observation told that this will be proportional, this is a proportionality constant, to the temperature gradient in the direction of heat flow. This temperature gradient is in the direction of heat flow Qx, and a minus sign is deliberately given because the heat is flowing along the negative temperature gradient. To make the heat flux positive directions to be identified, we give a minus sign, and this is in analogy with all phenomenological equations or laws, like electrical current flows along the negative potential gradient, like mass transfer takes place along the negative concentration gradient. So therefore, to identify the positive direction of the flux, we give a minus sign, so that the positive direction of the flux is associated with the negative gradient of the potential. Now the question comes here, it is a very simple case, but in practice temperature may be a function of that, that means there may be a temperature variation in this direction also. Why? If you consider this as y direction. If temperature is a function of x, not of y, if you consider this also as the y direction, then at all points temperature gradient will be same, heat flux will be same. Similarly, if it is not a function of z, at all points will be same. But in practice, temperature may be function of all the space coordinates with reference to a frame. For example, in a Cartesian frame of reference, temperature may be a function of x, y and z, and all these things today what I am telling is at a particular instant. So time also will come as an independent variable. So it may change with time. Now we are thinking of spatial variation of temperature. So at any instant, we just concentrate at any instant. So temperature may be a function of all the three space coordinates. Then in that case what happens, at any point there will be a heat flux in this direction, there will be a heat flux in this direction, and there will be a heat flux in this direction at a point. That means these are the respective heat flow per unit area normal to that direction, say limiting value as the area tends to 0. And in that case, Q is represented as a vector Qx, where I, j, k are the unit vectors along x, y, z directions with respect to a Cartesian frame. Well, Q is represented as a vector. In that case, this law given by scientist Fourier can be written in a generalized form as Q is equal to minus k grad T, that is gradient of T, where grad T is given by okay. So that Qx becomes minus k, then del T del x, because a partial notation partial derivative has to be given. So in that case Qx is minus K, because T is a function of and this law Q is minus K grad T, this law is known as, according to the name of the scientist, Fourier's conduction, law of heat conduction. Fourier's law of heat conduction, and this forms the foundation pillar of the conduction and the convection heat transfer. That is the Fourier laws of heat conduction, that is Q is equal to minus K grad T. Here the constant K is a property of a system and it is known as thermal conductivity. Well, this is known as thermal conductivity. So K is thermal conductivity. K is known as thermal conductivity, and for an isotropic material K is same for all directions x, y, z. It is independent of the direction of the coordinate axis, as you know, and in that case K depends only on temperature. K depends, K is thermal conductivity, and Vt, K is thermal conductivity. It is a property, and for isotropic material it is independent of the direction of the axis, and in that case it is purely a scalar quantity, a scalar constant which is a function of temperature only for isotropic material. In this class we will discuss the things almost for isotropic materials, and this thermal conductivity in a broad sense is known as transport property relating to heat transfer. So the property which relates the transfer or flux of a quantity with the potential, with its potential causing that flux, is known as transport property, like viscosity, which relates stress with the rate of strain, diffusivity, which relates the mass transfer with the gradient of concentration. Here rate of strain is difficult at the first moment where the gradient is coming, because rate of strain is defined in terms of the gradient of velocities from the kinematics of fluid flow. Well, so therefore this is known as, in broad sense, transport coefficient related to heat transfer, thermal conductivity. Now the unit of thermal conductivity is very simple, because heat flux divided by the temperature gradient. The thermal conductivity unit will be heat flux divided by temperature gradient. Now in SI, heat flux is defined as unit of K. Heat flux is defined as heat flow per unit area, watt per meter square. And what is temperature gradient? It is degree Celsius or Kelvin, any one of these two, divided by meter. So therefore the unit is watt per meter degree Celsius or watt per meter Kelvin. This K is not thermal conductivity, it is Kelvin, and Kelvin unit is not written in terms of degree Kelvin, whether it is a change in the Kelvin or it is the absolute Kelvin. You understand? If you change the temperature from 460 Kelvin to 480 Kelvin, what is the change in temperature in Kelvin? 20 Kelvin, sir. And what is the temperature of the body? 460 Kelvin, not degree. Okay, so therefore it is written as Kelvin. So this is degree Celsius. So this is the unit, either this or this. Clear? Now I will time left is less. So before I finish this, I tell you this part I will extend afterwards, that the cause of thermal conductivity or thermal conductance in different material. As you saw here, the thermal conductivity is a property which allows the heat to flow. For a given temperature gradient, more is the thermal conductivity, more is the heat flux. Now this property of thermal conductivity is due to what? Is attributed to certain molecular level physics, because any macroscopic property, whether it parameter rather, whether it is a property or anything else, we define through the molecular activities. Now the cause of this thermal conductivity in case of fluids comprising liquids and gases are different from that of solids. In liquids and gases, the heat is conducted by the energy transfer between the molecules because of its collisions. Molecules are always in a state of ceaseless motions, as you know, and this motion comprises translational motion, also the rotational and vibrational motion about its own axis, and because of which all molecules have kinetic energy. When a molecule is activated to raise its temperature, its kinetic energy is actually increased, and because of random collisions between the molecules, it transfers the kinetic energy to the neighboring molecules, which gain the kinetic energy from the upstream molecules which collides with it, and there is a random collision in all directions, and because of this collision, when this kinetic energy is transferred, we conceive this as the heat transfer. So therefore a fluid, liquid or gases having high thermal conductivity means the collisions for these molecules of these fluids at a given state property is more compared to the other. So therefore this energy transfer due to the collision is the mode of heat conduction in liquids and gases, and conductivity arises out of that, the property. In solids it is little different. This is because in solid, as you know, the basic difference with the liquid and gases is that in solid the molecules are closely packed, the mean free path is extremely small, and the cohesive forces are very strong. The way we have seen the viscosity effect in case of liquid and gases are different. Similar way here it is not the collision, rather it is attributed by two phenomena. One is the flow of free electrons, another is the propagation of lattice vibrational waves. What is flow of free electrons? Flow of free electrons takes place in case of metals. In metals, the molecular arrangement is such that there are free or valence electrons, you have read in chemistry, that which form a cloud in the periphery of the atom. They are not within the atom, and they share with the other atom of other element in the reaction. This cloud of electrons is known as free or valence electrons, which are there in all metals, which take part in conducting the electrical current, flow of these free electrons from the electron cloud, and at the same time they take part in flow of enhancing the flow of heat due to conduction. So therefore, for this reason, a metal is a good conductor of both heat and electricity. And the lattice vibrational wave part is suppressed there. But there are highly ordered crystalline non-metallic substances where the lattice vibrational part becomes prominent. What is this? So in those types of solids, non-metallic solids, the molecules are arranged in an order, in an array, a set type of thing which is known as lattice. Probably you know these things, I am not going into details of this. And there the molecules starts vibrating in a very synchronous way. As a whole, there is a lattice vibration which is propagated within the material, and that is known as lattice vibrational waves. You don't have to know much in depth of it because this is not our course, this is for your information. And for those highly crystalline non-metallic solids, especially for, I am telling examples, diamonds, graphite, silicon, quartz, this lattice vibrational wave propagates, and that propagation makes the major contribution, not the free electrons, to the conduction of heat. And sometimes this becomes so high that these non-metallic solids exhibits more thermal conductivity than the metals, but electrical conductivity, they are very poor. They are bad electrical conductor, but good heat conductor. And that's why they are used for cooling of electronic component, and they are known as semiconductors. Now with this I will just show some for your ranges of thermal conductivities of materials for your information. This is nothing great, you just have a look the range of thermal conductivity of the materials. Where it is? তুমি এটা করে দাও না, তুমি এখানে এসো। So you see, just have a look only thermal, তুমি দাও, you just stand there. This is the range of thermal conductivity. I don't know whether you can see from the back. You see, this is the thermal conductivity axis, watt per meter K. This is 0.1, this is 1, this is 10, this is 100, this is 1000. And you see hydrogen, helium, air, carbon dioxide gases, they are within that range 0.1 to 0.05, like that, a little bit 0.6. Then comes the insulators, fibers, wood, then this is foam. Then comes the liquids, mercury, water, oils, they are in the range of 6, 7, 8, that is between 1 to 10, and for some oils little bit of 1. Then non-metallic solids, some oxides, rock, they lie in this range. It is done 50 to even below 1. Then the alloys, aluminium alloys, bronze, steel, nichrome, these alloys fall within this range 100, little more than 100 or below 100. Then comes pure metals. Copper is one of the very good heat conductor whose thermal conductivity is somewhere near 400. And you see those non-metallic highly ordered crystalline materials, that solids rather, that is diamond, graphite, silicon, quartz, their thermal conductivity even up to 1000 watt per meter K. They show such high thermal conductivity. Next is, this is some representative figure of thermal conductivity variations with temperature. This is for liquids, ammonia there is a strong decreasing trend. This is for gases. For hydrogen and helium there is a strong increase, strong influence of temperature in increasing the thermal conductivity, whereas for air the thermal conductivity is lessly influenced by temperature. Then it is water and carbon dioxide. Okay, next is, these are just for your understanding. For solids, you see the thermal conductivity of different solids are there. Not much of a difference. For some solids there is a sharp decreasing trend. For silver, copper, aluminium, these are very important. The influence is not very marked with the temperature, the thermal conductivity change. Okay? So these are certain information that how the thermal conductivity varies with the temperature. Okay, thank you for this class.